Hello, my name is Alvaro and I'm going to talk about a Vitali covering theorem for Hausdorff-type measures in uniform spaces. By reviewing the literature, we can find at least two Vitali covering theorems, aside from the covering lemmas, one for the Lebesgue measure and the other for the Hausdorff measure. Both of them apply to Euclidean spaces, even though the second one could well be valid in general metric spaces. However, there does not seem to be any concerning uniform spaces, which are a natural generalization of metric spaces. Here we propose a version of this classical theorem for uniform spaces. We will begin by recalling the classical version of these theorems. Then, we will recall the definition of uniform spaces and we will introduce the linearly uniformizable spaces. Next, we will recall a pre-existent Hausdorff-type measure for uniform spaces. This will make us propose a generalization of the diameter function. Next, we will talk about Vitali classes and how to translate them to uniform spaces. And finally, we present our main result. So, let us begin by reading both classical Vitali covering theorems. So, the first one says that let's take E a subset of R to the D, which is measurable and has finite Lebesgue measure. And let V be a regular family of closed subset of R to the D, that is a Vitali covering of E. Then, there exists a finite or countable infinite disjoint subcollection from V, such that those points not covered by this subfamily have zero measure. And the version for the Lebesgue measure says that let E be a subset of R to the D, which is measurable, and let V be a Vitali class of closed subsets for E. Then there exists a finite or countable infinite disjoint subcollection such that either the sum of the diameters of the power of the diameters is infinite, or those points not covered by this subcollection have zero measure. We see that both classical Vitali covering theorems state that if we have a measurable set and a Vitali type covering of such set, we may select a countable or finite subfamily of such covering, verifying that the points not covered by this subfamily have zero measure. In case we use the Hausdorff measure, it may happen that the sum of the diameters of the subfamily is infinite. Thus, the version concerning the Lebesgue measure is kind of stronger, but the one concerning the Hausdorff measure is more general, since it could well be valid in general metric spaces, and not only Euclidean spaces. We now recall the definition of uniform spaces. A family of subsets of the product of an unempty set X with itself is said to be a uniform structure if it is a filter, the diagonal is contained in each set. For each set, its inverse is also part of the uniform structure, the inverse defined this way, and a certain triangular inequality type property is verified. This is defined using this composition here. These sets are called entourages, and we will say that a family of entourages is a base of uniformity or a fundamental system of entourages if it is a base of filter. Besides, every uniform structure induces a topology following this construction. We say that a set A in X is open if and only if for each X in A there exists some entourage such that this set is contained in A, where this set U of X is defined in this way, and we may also define this other set where instead of having one single element we have a whole set. Finally, a uniform space is said to be linearly uniformizable if it admits a base of enturages that has a linear order with respect to inclusion. We show now two instances of linearly uniformizable spaces. The first one is a uniform structure derived from a metric space. So, for each epsilon greater than 0, we define U sub epsilon this way, as the point whose distance is lower than epsilon. It can be verified pretty easily that this family is a uniform structure, and furthermore, they are trivially ordered by inclusion. If epsilon is lower than delta, then U sub delta is contained in U sub epsilon. And for the second one, we consider an empty set S and a well-ordered set I. We define these sets V sub beta, and it can be verified that they establish a base of uniformity with a linear order. So they are also a linearly uniformizable space. We move on to measure theory in uniform space. We move on to measure theory in uniform spaces. It is not deeply developed, but fortunately, it is not totally empty. Richard Wilmot proposed a Hausdorff-type measure for uniform spaces. It is constructed the following way. So, we first need a family of subsets of X, such that the empty set is there. We also need a mapping tau, a non-negative map, such that tau in the empty set is 0, and given an entourage U, we define this set. Then we may define mu sub U of A at this infimum, where those C are covering of the set A, and we define mu of A at this supremum, where the supremum is taking over all the entourages of the uniform structure. We immediately observe that it naturally generalizes the Hausdorff measure for metric spaces, but instead of measuring the sets of the covering using the diameters, we use the entourages, and what we add is the value of the map called tau instead of the power of the diameter. And it can be verified that mu is an auto measure on X. In the construction of the usual Hausdorff measure, this tau, as we already said, is a power of the diameter. However, we don't have a metric here, so we need to set some conditions on this tau so that mu has desirable properties. Wilmot proposed several conditions on tau. He proposed 4 or 5 conditions, but we will only require these 3. We need that tau in the empty set is 0, as we previously mentioned. We also need that if A is contained in B, then tau of A is lower or equal to tau of B. And if tau of A is 0, then A may contain at most 1 element. In addition, we will require these 3 extra properties we developed by ourselves. So, we take a base of entourages V, and our family of subsets of X is going to be this type of set. And we require that tau of U of X is 0 if and only if this product is contained in the diagonal. Also, for each entourage U in the base and each X in X, there exists a constant C of n that only depends on n. It does not depend on the entourage, neither the point, only on n, such that this equation, this bound, is verified. And finally, we define a property we call sorting that said that for each 2 entourages U and V in B, and each 2 points, if this condition is verified, then one entourage is contained in the other. And we see that this property may only be defined in linearly uniformizable spaces, because for any two entourages, one is going to be contained in the other, and this is saying that the space has a linearly uniformizable structure. So next, we'll recall the definition of a Vitali class. Given a set E in a metric space, a family of subsets V is said to be a Vitali class for E if for each point x in E and each epsilon greater than 0 there exists some S in V such that S contains x and the diameter of S not being 0 is lower than epsilon. That is to say, for each point from E there is some set in V having arbitrary small diameter. We extend this definition to uniform spaces by controlling the size of the sets using entourages instead of the diameter. So given E a subset of X, we say that V is a Vitali class for E if for each X in X and each U there exists some S such that S is a neighborhood. S contains X. S contains more elements than X and is of size U. And a trivial example of this is this one. It's just to take all the sets of this form. It is a Vitali class for E. Also, besides, we will only consider Vitali classes of this form, where we take the closure, the topological closure of this set of V of X, where V is a symmetric entourage of a given base of uniformity. Lastly, we will say that a Vitali class is tau upper close, well, strongly upper tau close, if when we subtract a finite family of sets, the remaining sets still reach the supremum of tau evaluated in those remaining sets, and the set where it is reached cannot intersect any member of that family we subtract. So this definition here. We are now prepared to show our main result, but first we need a condition between tau and mu. We will say that mu is exhaustively null with respect to tau if this implication is satisfied. So we have this sequence where these are entourages from a certain base of uniformity, and we will say that mu is exhaustively null with respect to tau if when this sum is finite we have this limit, this mu of u of these sets tends to 0 as k tends to 0, and it must be verified for each u in the base of uniformity. Well, we see that linearly uniformizable spaces, we have a proposition that said that linearly uniformizable spaces, when the tau is sorting, they verify this proposition here. So if we have a uniform space with a tau mu measure referred to a base of symmetric entourages, if tau is sorting, then mu is exhaustively null with respect to tau, but tau can only be sorting in linearly uniformizable spaces. So linearly uniformizable spaces provide a good example of spaces where mu can be exhaustively null with respect to tau. But there may be some other examples of uniform spaces which are not uniformizable, linearly uniformizable, which may also verify these conditions here, for mu to be exhaustively null with respect to tau. The linearly uniformizable are a good example, but there may be some other examples which are not linearly uniformizable. So finally, going for our main result. Well, let's read it. Let X be a uniform space endowed with a tau mu measure where mu is exhaustively null with respect to tau. And let E be a subset of X. If V is a strongly upper tau closed Vitali class for E, then we may select a disjoint finite or countable infinite subfamily from this V such that either this sum is infinite or those points not covered by the subfamily have zero measure. Well, let us compare these two versions, the classical version of the for the classical Hausdorff measure and our version of the theorem. We see that in both of them we need a Vitali class of sets, and in both of them we have two options. Either here the sum of the diameters is infinite, well, a power to the s of the diameters are infinite, and here what is infinite is the sum of the values of tau. Or the other option is that the set is almost covered. Those points not covered by the subfamily have zero measure. They are pretty similar one to the other. The main difference is that here we only need a Vitali class of closed subset. We know we have very few other requirements, but here we need for mu to be exhaustively null with respect to tau, and V must be strongly upper tau closed. The reason for this comes from the proof of the theorem. The idea of the proof of the classical version is to increase the size of some balls in order to capture some points not initially covered by the smaller ball. As we say, if we increase the size, it covers those points. But in the uniform space, we lack some good properties of the metric, and thus we need a larger class of sets in order to guarantee we capture all those points. In metric spaces, we only need to make the sets bigger, but in uniform spaces, we cannot make those sets bigger. We need to have more sets in order to capture those points, in order to have this almost all. Therefore, even if the uniform version of this theorem is also valid for metric spaces and Euclidean spaces, the hypotheses are unnecessarily strong for metric spaces, but we cannot leave them out in uniform spaces. So this theorem is also valid in metric spaces and in Euclidean spaces, but is unnecessarily strong, the hypothesis. So we finish here. This is the theorem. These are some of the references we used for this result, and with little to add. Thanks so much for your attention.